Oh, maybe there's something else going down at Dave's too.
All right, so this is number 4 or 5 in the homework for section 5. And we are trying to troubleshoot. So that's equal to 4, 2, 1. And the 4 comes from this group here. So that's the U2 V3 minus U3 V2. And let's pick a different color. The 2 comes from the outer 2 columns. So that'd be U1 V3 minus U3 V1. And the 1 comes from the first 2 columns. So that would be our U1 V2 minus U2 V1. All right. We are trying to find the cross product of U minus 3V and U plus 2V. So what is that going to look like? Switch color. That's going to be I, J, K, and U minus, so that's going to be U1 minus 3V1, and U2 minus 3V2, and U3 minus 3V3. And then U1 plus 2V1, U2 plus 2V2, and U3 plus 2V3. Do we have any clever tricks for determining the new cross product? We have a linear combination of vectors in both cases. So by the way, a linear combination is when you add or subtract a pair of vectors, and you can also multiply by constants. As long as you don't multiply the vectors together, which is weird because that's either a cross product or a dot product for now. So linear combinations are pretty common. Let's just consider the first component of this cross product, which would be blocking out the first column. Ooh, that's messy. U2 minus 3V2 times U3 plus 2V2 minus U3 minus 3V3 times U2 plus 2V2. Eek! And that's just the first component. Multiplying that out, what do we get? We get U2, U3 plus U2, U2, V3 minus 3V2, U3 minus 6, oops, V2, V3. That's that one, and then we'll have to subtract. There's got to be an easier way to do this. Oh, wait, this might work out nice. U3, U2 plus 2 U3, V2 minus 3 U3, U2 minus 6 V3, V2. Does stuff cancel here when I do that subtraction? This one goes.
Almost every term cancels.
That's U2, that's U3. Here's a no. Is there another U2, V3 down here? Okay, and those guys cancel right there. V2, V3. Oh, wait, did I mess that up? Oh, that must be a V3, V2, V2. Okay, yep, those cancel. Okay. And then these guys are just different. Now here we have a UU. Did I make a mistake? Should we have a VV? Did I get that right? Let's see. So that was, double check I wrote those right. Ignoring that stuff, U2, V2, U3, V3, U2, U3, okay. And then V2, this right here, that should be a U, no.
Oh, on the bottom.
This should be a,
changed.
this should, I think this should be a V2, V3.
No, that one's right. It's the one directly below it. Another.
That one's incorrect.
Should be V3.
That should be U3, no, V3, V2.
Not U3, U2.
V, oh, it should be V3, U2. Yeah, you're right, V3, U2.
And then
yeah.
it would cancel partially with
Okay, so that's a V3, U2.
It would cancel partially with the 2.
No, it'd be added on to.
Oh, yeah.
So that's like this one right here.
So those two would,
Okay.
those two add together.
All right, so this then, so these two match, right? So we're going to have a 5, yeah, U2, V3, and then a minus 5. All right, that's U3, V2, which is 5 times this guy right here, right? Yeah, and the other ones are going to behave exactly the same way because we have the same set of constants. So what this is going to lead to, yeah, it's going to lead to 5 times the original cross product, U cross V. Okay, so then the question, is there a more clever way to do that besides brute force? Kezia, you did this one already. Did you find a more clever way to do it? You watched the YouTube video on it, and they had a more clever way there?
Yeah, they had like a formula.
They had a formula for it. Let's check it out. So did this one, I don't think this one came with a video. Was it back in the problems? Oh, you just YouTubed the cross product to see? Okay, so I'm gonna go, let's see, let's go into a new tab here. Oh shit, I didn't mean to do that. Oh well. And cross products. So let's check out the textbook. If there's anything in there. All right. Oh, no. Does that help? Maybe. Let's see if those rules help. Let's see, is there anything else? I think that's probably all we have to work with. The arithmetic rules for, yeah, that's it. Okay, so where'd they go? Right there. So let's screenshot that and see if that helps in cleaning this up at all. We really don't have a constant multiple of the whole cross product anywhere. And we have the product of a difference.
So maybe.
Oh, yeah, I think E will help us out here. So let's take this to a new screen, Control C, Control V. And then the rule I want to steal, let's go back here, is, I think it's going to be that one, but it could be the one above might help too. Or screen clipping, there it is. Let's grab both of those, but I think it's the bottom one that I want. So this says if I have a vector crossed with the sum of two vectors, then I can distribute that vector through there. Well, I can distribute this through. So let's see, will this help? So this is just a new vector, right? Linear combination. So let's call that for a second vector A. So then I can rewrite this as A cross U plus A cross 2V. And then the rule above says I can pull that 2 out. So this would be A cross, oops, U is a vector, A is a vector, A cross U plus 2 A cross V. Now A is really that difference up there. So rewriting that, let's see if that helps. I have U minus 3V times, or crossed with, excuse me. Let's make a little more room for that. Crossed with U. And then over here, we'll have plus 2 times U minus 3V crossed with V, which we can then bring together. So that's going to give me U cross U minus 3 V cross U plus 2 U cross V minus 6 V cross V. Did I do that right? I missed a cross somewhere. Yeah, cross, okay. Now, if you change the order of the cross product, that changes the sign. So this right here, we could rewrite as plus 3 U cross V, because remember the right-hand rule just changes the direction of the vector, which is positive or negative. So then these two in the middle combine to 5 times U cross V. And when you try to cross a vector with itself, you get 0. So these guys are just zeros there and there. Yeah, so we could use some vector arithmetic and show, yeah, we get 5 times the original cross product. So we did the easy way and the not so easy way. I guess neither one of those was easy really, was it? So it's kind of interesting. This is similar to the rules with variables, but there's some extra tricks. Like in regular multiplication, you can just change the order all you want and it doesn't matter. But in vector stuff, if you change the order of the product, it changes the sign of the answer, which is interesting. And then crossing a number with its crossing a vector with itself is always going to give you 0 for the cross product, because you don't have a plane to be perpendicular to. Is kind of the geometric way to think about it. Well, that was fun. All right. Another one. Let's see, where was that? Over here. 5-5 homework. No, 11-5 homework. That was 5, 6. All right. Find the area of the triangle. So this one's pretty cool. To make this work right here, let's see. Anytime I have 3 points, I have a plane if they're not collinear, and 3 points make 2 vectors. So basically we have to turn this into 2 vectors to make the triangle. So you decide how you want to work the 2 vectors. I wanted to do one like this yesterday, but we didn't get to it. So let's steal that. I'm going to take a better screenshot of that. Blow you up a little more. Ooh, yeah, that's big. Screenshots. Come on. So this one is hard to draw without some kind of 3D software or special graph paper, but it's not too bad. So let's give it a shot together. First, let's see if we can draw this. So what I'd recommend for drawing it is often when people draw 3D stuff, they make a vertical line for Z, and then coming out at about 120 degrees, we make an x-axis and we make a y-axis. That's X, that's Y, and this is Z. And then we want to try to plot these points. And so often I'll put dotted lines to indicate like Y going back, X going back, and Z going down. Then make some kind of scale. We need to get up to 6, -5. So maybe 1, 2, 3, 4, 5, 6. And because these are kind of like sticking out, the foreshortening is going on. So if you're trying to get the units to match with X, Y, and Z, that's a little bit tricky. You kind of need hexagonal paper to do that. I'm not going to worry about it too much. Let's see. So just a little practice here. So we want the vector -3, 1, 2, 3. Let's use a different color. So I'm going to go back 3 units. I'm going to go 3 units for Y. So 1, 2, 3 in the Y direction, trying to match up with these guys. And then I want to go up 6. So 1, 2, 3, 4, 5, 6, something like that. And so there's 1 point somewhere up there. Q, let's use a different color. How about green? Maybe -2. So 1, 2, -1 back that way, and then up 1, 2, 3, 4 units. So I'm just kind of guessing. So there should be a point around there. And 6, what am I going to use? Black maybe? 1, 2, 3, 4, 5, 6 for X, -5 for Y. So back this way. Uh-oh, I might go off my screen. That's definitely going off my screen. Darn it. See if I can grab all of this. Almost got it. Oop, too much. One more try and then I give up. Oh, well, I got everything. Seriously? Technical difficulties. Slide over. Okay. Back to black. So let's see, we go -5Y. So 1, 2, 3, 4, 5. Why can't I draw that direction? All right, there's my negative 5y, and then z drops down 1. So I have a point somewhere over there, three-dimensionally. So what I need to do based on those points there, let's use, I'm running out of colors, blue, I guess. I want to pick one of them as a central point and then make vectors out to the other two. So maybe I'm going to pick Q as my central point, and I need a vector going out over there to R. That's Q, and I need a vector heading over here to P. Once I have those two vectors, does anybody remember what operation on those vectors gives me area? The dot product, excellent. The dot product does. So what the dot product does, if we take the plane those guys live in, so let's make believe we're looking straight down on the plane. I'm going to have this vector over here that's going to be called QP. And then I'm not sure about the angle in between, but say say that vector right there is my QR. What the dot product does is it pretty much creates a parallelogram based on those two vectors, and the dot product of those two, so QR dotted with QP, is going to give me the area of this parallelogram. So then we just divide that dot product by 2. Yeah, so what we have to do here is find the vector QP, which is a subtraction, P minus Q. The vector QR would be R minus Q. And then dot those two together, and that'll give us the area of the parallelogram, and then cut it in half. So the vector QP is going to be P minus Q. So P minus Q. So -3 minus -2 is a -1. 3 minus -1 is 4, and 6 minus 4 is 2. So that should be the vector QP. QR is going to be R minus Q. So 6 minus -2 is what, 8 on a good day. -5 minus 1 would be -4. And -1 minus 4 would be -5. Is my arithmetic all right? So dotting those two vectors and dividing by 2 should give me the area of the triangle. So I want QR dotted with QP over 2 for the area of the triangle. So what's that going to give me? That's, and I want the magnitude of that, by the way, absolute value. So -8, -16, -10, all over 2 is what? 24, 34 divided by 2 is 17. Anyone else getting that? Square units. So just by the way, drawing this 3D picture didn't help us at all in finding that area. I just wanted to practice drawing a 3D picture with you guys, that's all. It's kind of challenging. It's really nice to do it in GeoGebra because then you can rotate it to get a better view of it. And GeoGebra has a way to turn that into a plane so you can see what the plane looks like too. And then remember that tool I showed you in GeoGebra the other day, given a point and a vector, you can create another vector in that direction. So for example, in GeoGebra, I could have it draw these two vectors right here. If I put a point here and here, I can then tell GeoGebra to draw this vector for me and that vector for me so I can see that object there. So GeoGebra is kind of fun to play with. I highly recommend messing around with it some more. All right, let's try another one. What else do we have for interesting problems? The parallelepiped. So parallelepiped is, what's that? Yeah, so that one's very similar. What you have to do is, and it doesn't matter what order you do it, you pick oh, they give us all three vectors. Yeah, so all we have to do is take the cross product of two of the vectors in absolute value, magnitude, and then we dot it with the other vector, and then that's going to give us a new vector that we then take the, let's see, did I get that right? No, we do cross product first, and then the dot product, and then we take the absolute value of that. Yeah. So I'll just write that down quick and leave you to do that later. Let's see, screen clipping, new page. So one way to solve this problem would be to say find the dot product of B and C, or cross product, excuse me, I keep messing that up. That's going to give me a new vector, and then if I dot that with vector A and consider the absolute value of that, that'll give me the volume of the parallelepiped. So that's not too bad.
Does it matter which one you dot?
What's that?
Which vectors you dot?
Yeah, that's a good question. We do have to consider the right-hand rule to do that. Otherwise, well, no, we don't, because we're taking the absolute value of it in the end. Yeah. So what would happen is if we crossed B and C in the wrong order, they would give us a vector facing away from A, which means we would end up with a negative volume, which absolute value gives us the positive version. Yeah.
Or you did like B and A and then
It shouldn't matter. Yeah, so this should give you the same exact volume if you do something like take the B and the A cross product and then dot that with C. You should still get the same answer. Yeah. Because if you, let me try to draw a picture of why. That should work out okay. So let's say that's one vector and that's the other vector. Maybe that's my BC right there. Based on BC, I can, oops, I wanted a different color. Let's go red. I can turn them into a parallelogram, right? And then I have some other vector, let's say A heads off in maybe this direction right here. And then based on A, I can combine it with parallel vectors from intersections, and that's going to create my parallelepiped. Let's see. I'll dot those because they're in the background. So there's my parallelepiped. And if you think about this thing right here, there's a lot of ways to go about finding its volume. If you consider this top portion to be the base, then you find its area and you multiply that by the perpendicular height to the opposite base. Alternatively, there's no reason you couldn't say, hey, this face right here is going to be my base, and then I want to find the perpendicular height heading in that direction, which this does no matter what. Okay, so it doesn't matter what order you dot and cross them in, it's just a different perspective on that 3D figure, which one you decide is the base, and then where the height extends from there, which is kind of awesome. All right, what else do you guys want to look at? What's that? Polar stuff? Yeah, we haven't done polar in a long time. Let's take a look at polar. All right, so just a reminder, I put in a, let's zoom out a little on that and minimize that. I put a final exam block in our course, and there's the printable final exam that I made, which is like the exam you will see, but this is like 10 times longer. There's a solutions forum here, so if you solve a hard problem, put your solution up there for other people to see. Like take a picture of it and post it. And then this is the My Open Math version, which is similar to homework problems you've had before. And I would say priority is doing this one first and then looking over here for more practice problems. Or you can go back and all your homework is still open for review. You can go back and poke around there. So let's back up. And I also think we should do a Taylor remainder problem today before we part ways. All right, so let's see, polar. Tangent line and polar kind of sucks. let's do an area. So what'll probably happen on the test is I'll pick on a particular function like this one right here. And notice I used the same function in the next two problems so that we know what we're working with. So let's start off by graphing the function 2 plus 2 cosine theta. And to do that, I would recommend a couple of different things. Let's see. GeoGebra does not do polar very well, so we have to go to Desmos. I would make it in a graphing calculator and then transfer that onto paper and label a few angles. So I want 2 plus 2 cosine of, and I think I can just type theta, right? It's been a while. Oh, I have to put an R equals. Yes, thank you. R equals. Okay, so there I get this sideways heart or butt, depending on your mood. And so we want to go about coming up with a graph for that. So I can see it ranges out to 4 that way, almost to 3 up and down. The radius is extending from this midpoint right here. So I should then transfer this graph to paper and then label some coordinates of it. So I'm going to cheat a little bit by copying that instead of drawing it by hand, since I have the computer in front of me. And so what I want to do next is just label some values of theta. So I believe that is the graph of r equals 2 plus 2 cosine of theta. And so let's see, if theta is 0, cosine of 0 is 1. So that gives me this point right here. So I'm just going to make a note, that's when theta is 0. If theta is, say, let's pick something easy like pi over 2. At pi over 2, cosine is 0, so r is just 2. So that point right there is probably a radius of 2. Does that make sense? I'm coming up with that. So that's about theta equals pi over 2. At, let's see, pi, cosine of pi is -1, so that's going to give me a radius of 0. So that point right there must be theta equals pi. And I'm starting to get the feeling I'm going to have some nice symmetry going on here. So I'm guessing that's 3 pi over 2 right there. And cosine of 3 pi over 2 is 0 again. The angle 3 pi over 2 points me straight down, and there's a radius of 2 pointing straight down. So yep, that right there is theta equals 3 pi over 2. So it looks like the curve is being traced out in that manner, which seems pretty straightforward. And the period of this sucker is what? Period is 2 pi. And polar stuff is weird. You got to play with it to see what the period is. You can't just look at it and say, oh, period's 2 pi or pi over 2. You got to plot some points and see. All right, now that we've done that, let's do the area problem. So we want to find the area inside this. I don't really need to do the whole thing. I can just double halfway around. So I could just do twice the integral as theta goes from 0 to pi. Does anybody remember the area formula? Mm-hmm. Now it's just 1/2 r squared to theta is the formula. And that comes from looking at the area of a sector of a circle. Okay, so if you ever feel like, oh man, I can't remember that, what you do is think about sector of a circle. So here I have some angle. I'm going to call that angle d theta. And I have a radius, and let's assume it's the same radius because it's a circle. I want to know what is the area in there. Well, I know the area of the whole circle, oops, back here, is what, pi r squared, right? Okay. And what I want to do is figure out what fraction I have here. Well, what is a complete revolution in radians? 2 pi. So the fraction of the circle I have is that angle, d theta, out of 2 pi. That's the fraction of the circle I'm displaying right here. Right? And that's the nice thing about radians. Fractions of circles are just the radian measure divided by 2 pi. Cleaning that up, the pi divides out, and all I'm left with is 1/2 r squared d theta. Okay, so it's just the definition of the area of a circle sector. Area, circle, sector. circle. There we go. All right, so now we just have to come up with this. Now the 1/2 and the 2 balance nicely, and so all I have to do is square that sucker right there. So let's do that. New page. So I want the integral from 0 to pi of the square of, 2 plus 2 cosine theta d theta squared, which is going to give me a 4 plus 2 times 2 is 4. To get 2 of those, 8 cosine of theta plus 4 cosine squared theta. And 4 is no problem, 8 cosine theta is no problem, but the cosine squared is a problem. So anybody remember what we do with that? Is the half angle formula. So let's see, half angle formula tells us that the cosine squared of theta is equal to, is it 1 minus or 1 plus? I think it's 1 plus cosine of 2 theta over 2. All right, let's double check trig identities. We seem to be a little rusty. Trig identities. And sure, Wikipedia, what do you got for us? Half angle. Yeah, the cosine is the plus, the sine has the minus. And then we have a theta here and a 2 theta there, the way we're viewing it. All right, so back to the notes. Yep, that's right. So then subbing in here, we're just going to replace that. Now the 4 and the 2 will cancel each other a little bit. So that right there is going to become twice that. So I'm going to call it 2 plus 2 cosine 2 theta. And I'm just crossing it out because I'm too lazy to rewrite the whole thing. All right, so that 2 is going to combine with that 4 to give us a 6. And we're ready to find an antiderivative. Okay, so antiderivative of this sucker is going to be a 6 theta plus an 8 sine. And then I do have the multiple of 2 outside of the cosine there. So that should just be plus sine of 2 theta for that last chunk. Anytime I do some kind of jiggery pokery with constants, I usually double check by taking the derivative to see what's the derivative of the sine of 2 theta. It'd be 2 cosine 2 theta, so yeah, it works. So I always double check myself because it's easy to mess up those constants, and those are those little things that bite us in the butt. All right, let's see. Sine of pi and sine of 0 are both 0. So these terms are irrelevant. They're zeros, so it looks like I just get 6 pi as the answer, as that area. And what can we do to double check that? Not much. Integral calculator could help double check that we found the correct antiderivative and evaluated it correctly. Otherwise, I don't think I have any tricks up my sleeve for checking. You guys got any tricks up your sleeve for checking? Well, did we set it up right? Do we have the right formula? And then check with something that does numerical integration to see if it comes up with an answer in the ballpark. So that's about all we got there. Not too bad. We just had to remember that formula related to that area of a sector of a circle. All right, what else should we do? Taylor series problem? Okay. I was thinking, let's see, I asked a problem down here about the arc tangent. I thought that'd be probably a good one to do. What series is this up here? Anybody remember? That's the series for E, and let's blow it up, sorry, so you can see better. That would be E to what power? What's that? Nope, not e to the n. Almost. E to the power -1, correct. Yeah, that'd be e to the power of -1 because the e to the x is equal to x to the series of x to the n over n factorial. So all we did was replace the x with a -1 here. That's all I did. Okay, so that one's pretty straightforward compared to some of the tricky homework problems you had. All right, so I want to do arctangent to the nearest thousandth. Does anybody off the top of their head remember the arctangent series? Yeah, it's come up before. We derived it in two different ways in class. One way was by manipulating a geometric series. The other way was by taking repeated derivatives of the arctangent. Yeah, which was way harder than the other way. So what we're going to do is we're going to develop it. So new page. So does anybody remember about integrals or derivatives of the arctangent? What is it? 1 over 1 plus x squared is what? The derivative of the arctangent. So the derivative of the arctangent is equal to 1 over 1 plus x squared. Now, 1 over 1 plus x squared is kind of sort of related to 1 over 1 minus x. So let's just build from there. So if I consider the function 1 over 1 minus x, that's the evaluation of our basic geometric series. 1 plus x squared plus x cubed, yada, 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 all the way up to x to the n. Keeps going forever. If I take the, let's see, I need to do a substitution to get a plus x squared here. So in place of the x, I'm going to drop in a negative x squared. So I'm going to sub negative x squared in for x. And so that's going to give me a series for 1 over 1 plus x squared, which is going to be 1 minus x squared plus x to the 4th minus x to the 6th plus I'm going to have a -1 to the n, x to the 2n as my general term when I drop negative x squared into x to the n. All right, so then what do I do with this to get the arctan? Reverse the derivative, so I integrate. So if I integrate that, I can perform term-by-term integration provided it converges. Okay, the endpoints are always up in the air. Okay, but inside the interval, I'm okay. What is my interval anyway here? No. No. What's the interval of convergence for the basic geometric series? Reverse that, less than. Yeah, so it has to be a proper fraction is the only time that'll converge. So x has to be some number that's in absolute value less than 1. So in other words, x has to be between -1 and 1. And it turns out that holds coming down. Substitutions mean you got to tweak it a little bit. What happens if I put an x squared in there? What's the absolute value of x squared less than 1 lead us to? Well, do I need the absolute value anymore? No. So I could just say that's x squared is less than 1. How do I get rid of a square? Take the square root. What's the square root of a square? It is the absolute value of whatever's inside. So I'm back to that same interval, it turns out in this case. You always got to double check that. And then anytime I integrate or differentiate, that could change convergence at the boundaries. Right now, this function right here diverges at each endpoint. Okay, but taking the derivative or integral of this series right here, I might get convergence at an endpoint. I just got to check when I get there. Okay, so I'm ready to do my term-by-term integration. So integral of 1 is x. Then I'm going to have a minus x cubed over 3. I'm going to have a plus x to the 5 over 5. minus x to the 7 over 7, yep. Coming down the line, I'm going to have a negative 1 to the n, and then I'm going to have an x to the 2n plus 1 divided by 2n plus 1. Based on this nth term, what is n starting with? 0, correct. If I plug in 0 here, that gives me the first power. If I plug in 1 here, that'll give me the third power, and so on. Okay. So this, just a note, n is going from 0 to infinity for this series. All right, let's check the endpoints. So we're not quite at the problem at hand. Checking endpoints. Oh shit, there's another class that wants to come in here. We're out of time for fun, darn it. Okay, so here's how we would proceed. It is a good idea to check the endpoints. That wasn't part of this particular problem. Here I just said approximate the arctangent to within a thousandth. I have 3 ways to do approximations. 1, the alternating series remainder. 2, integral test remainders. 3, Taylor's remainder theorem. Last choice all the time is Taylor's remainder theorem because it's a pain. This alternates, right? Yeah, so the alternating series test says, hey, just look at the next term in line. So figure out which term is going to lead you to be within 1,000. So we just set up an inequality to play with that. We already know that x has to be less than 1. So then we just kind of play around with that thousandth based on this denominator down there. So when is 1 over 2 to the n plus 1 going to be less than 1,000th? And that's an inequality we can solve. What if there was a factorial in the denominator? Can we solve that algebraically? No, it was just guess and check. That's all you got. All right. All right, so we're out of time for fun for now. I'm around at 11 and 12 tomorrow if anybody wants to come play some more. Our official final time is Monday, I think. But if that doesn't work out for you for some reason, let me know and we'll do it at a different time.